sections of girders and things were thrown out at least like 50 miles an hour. Okay, and so the mechanism for all this happening is definitely a question.
Did that building catch fire, or was it radiant?
There were, building 7? There were fires on a number of floors, but it was not exactly, it's not what you think of as a building engulfed in fire.
How did they catch fire?
Okay, well, the official story is it caught fire from material ejected when the North Tower came down, and there were scars in the building from the North Tower hitting it. However, there's also some of the guys in our organization who have traced some of this down, and there's no photographic evidence of fire in Building 7 before noon. And so how would the North Tower have started the fires and yet not have them in evidence, not have them visible for another couple of hours? So there's also a lot of reason to believe that they were started in some other way. Okay, but the official story is they were started by the North Tower coming down. Basically, it's government security agencies. There were banks. There were Giuliani's emergency bunker was there. Carolyn?
All the stuff from Enron was in there.
Yeah, I think Laurel mentioned it. But the Enron records that, and supposedly it was the only copies. How convenient. Right. Okay. Now, the way I'm coming at this is sort of like a personal approach here. I'm coming at this as a physics teacher. I see things happen, and I say, how did that happen? And so this is a little, what I'm doing here is sort of illustrating a tool that I use in my teaching in that sort of a native context. Here I am at school, standing on a ladder with a soccer ball, and going, whomp, there's a physics experiment. That wasn't very smooth. Let's do it again. Boom. All right. Notice that this is a tool. What happens is you can go through it frame by frame and place little markers on something. And as you step through it frame by frame, like this. By the way, notice over here, if this jumps all over. Okay. That thing right there is tracing where it is on the graph. And so by tracing, notice you have to manually put these, excuse me, this, what I'm using as my mouse pad is causing this to jump. I don't know how I can fix that, but that's partly why this is so hard to control. Okay. So you get the general idea. This is a graph over here of position versus time, vertical position versus time. And notice that as I run it, if you watch this and watch the ball come down, it's like just watching a movie of the ball come down. But you can also do things like this. You can take, say, the vertical velocity. And notice this is a different kind of graph. And I want to explain this slightly because this is going to come into the picture in a few minutes. All right? As the velocity, if you look at the velocity as this thing comes down, it starts at rest, so it starts off at 0. Like the 0 there. And then as it comes down, it picks up speed. And it picks up uniform increments of speed in equal amounts of time. Okay? And that's the nature of what's called uniform acceleration. And that's characteristic of gravity. And so I wanted to let you see what that looks like. So we're graphing the velocity as a function of time. One of the things I can do is put this in an analyze mode. And you can start playing games with the graphs and the numbers. And so, for instance, I want to fit a graph to this. I'm going to select the range of data that I'm going to base it on. And I'm going to auto-fit this line. Let's make it a little bit more visible here. Hi. Hi. Aha. I just have a Self-Help Enterprises mouse pad. Thank you. And hey, it's working better. Great. All right. Self-Help Enterprises, by the way. Bard McAllister, for those of you who don't know it, was the founder of that in Farm Labor Committee under his leadership, founded the Self-Help Enterprises there. Okay, a forerunner in the sense of habitat and that kind of a thing, right? Okay. Notice that if I put a straight line through the data, and then you look at this little number down here, it says 9.70. If I try it again, if I take a few data points, notice it's trying to fit the line to the data, and data typically has a little bit of jitter to it. And so depending on how many data points I use and how accurately they were measured and all that, you're getting slightly different versions down here. And that's characteristic of any kind of data that you take in a measurement situation, okay? So, precise science is not necessarily one exact number. It's reasonably interpreting data, taking into account the kinds of errors that show up in measurement, okay? And notice this is 9.77 at this point right here. So this is very close to what would be considered the acceleration of gravity, 9.79 in this area, 9.8 a lot of places, all right? The reason I'm giving you that is that number is going to come back into the picture every once in a while. That's called G, or the acceleration of gravity, and it's also called free fall. And notice all we're talking about here is a soccer ball dropping under the influence of gravity, and this is how fast the speed builds up. So it's not correct to say how fast do things fall. When I drop something, how fast does it fall? Well, how about in the first tenth of a second, how fast did it fall? It was hardly moving, was it? It picks up speed as it falls farther, and so what's characteristic of falling motion is not what is the speed, it's what is the acceleration. What's the rate of increase of the speed? Is that clear? You have to have a little bit of a physics lesson if you're going to listen to me talk about 9/11. Okay. There we go. Anyway, so this is the kind of a tool, and the way I use it at school. Notice you can take lots of data and play all kinds of games with it much faster than when I was in school. We plotted each individual point with a pencil on a piece of graph paper. I still have students do that somewhat. Okay. Now, let's go back to 9/11. Let's play the same game with a building. When I knew about Building 7, I had already heard that various people had measured the rate of acceleration of the corner of the building and had, by various methods, determined that it had come down either at or close to free fall. Now, what are the implications of a building collapsing straight down at free fall? Free fall is like a soccer ball with nothing under it. If you have vertical columns in a building, you have a lot of material in the building. Then you have a lot of work to do crushing things as this thing is coming down. How is that going to happen at free fall? If you have energy due to the fact that all this stuff is stacked up high in the air, that energy gets transferred into motion. It's called kinetic energy once you get it moving. But if you have it doing things along the way, like breaking up concrete and steel and so forth, you're using some of the energy, and therefore it can't pick up as much speed as it would otherwise. And so the energy has to go somewhere, and it can't go everywhere. So if it starts off as what's called potential energy right now, if it is doing work along the way, it'll be coming down at less than free fall. What I did was I measured it. And so here I'm just playing it straight through. And this little corner right over here